welcome. And this is lesson 15 of the FPGA core. In this tutorial, we'll be talking about the receive control. This receive control is quite different from the receiver. We've talked about the receiver, and in our last tutorial, we talked about the transmit control. So in this tutorial, we'll be talking about the receive control. What is the receive control? So the receive control and the transmit control are part of the mark control status that is used for flow control when the FPGA core is operating in a full duplex mode. That is, it can send and receive at the same time. So assuming is the receiver is receiving piece of data and is busy and wants to stop reception of data doing full duplex mode, at that point it can transmit what we call a pause frame to the transmitter, telling the transmitter to halt data transmission, and the part of the receiver that sends this pause frame is called the transmit control, which is what we did in our last tutorial. And on the other end, the transmitter that was actually sending this data that needs to stop, that is the transmitter that received this pause frame, receives it using this module called the receive control. So in this tutorial, we're going to talk about the receive control. That is how the transmitter handles this received pause frame. That is, when the receiver receives a pause frame, that is when it's told to stop transmitting, how does it handle it? It handles it using this receive control we are going to talk about. So in this tutorial, we're going to talk about the receive control. You can find this the verilog code at projectfpga.com/tcp select receive control. So this is the logic sim circuit I'm going to be using for this tutorial. So first of all, as the major signal here is this signal. Okay, I'll have to simulate this circuit first. Let me turn on the clock. Okay, then so notice we have the MRS clock and the NTS clock. That is the transmitter clock and the receiver clock. Briefly, I'm going to show you why we use these two different clocks. So I'm using a single clock to clock them for the sake of this simulation. So we have the first very important signal, which is our detection window. Detection window means what the period of time at which we can start detecting a pause frame. We have our normal receiver, which receives our neighbors whenever neighbors are sent, but we also have the receive control, which receives only the pause frame. And for it to receive this pause frame, it has to receive it within the detection window. So this particular signal here, this signal coming out of this flip-flop, is the detection window signal. So that I'm talking about this signal here is the detection window. So very soon we're going to see how is being generated. It's not necessary to talk about it now, but we're going to see what this detection window signal is used for. I would like to explain how it's being generated towards the end of this tutorial, when we are going to be talking about the byte count 0. The byte count 18. You know, the byte counter counts from 0, 1, 2, 3 to until number 18. Just like every byte counter, the receive control, just like every module, the receive control also has its own byte count. So whenever the byte count counts up to 18, we are going to see how this detection window is being generated. But at this point, let's just use this signal. But note that this detection window signal is the time in which we can receive the pulse frame, and that's why it's called detection window, a period of that reception of control signal. So remember, this is our frame. This is the frame that was sent. So this tutorial we're going to see how these frames are being received, from the destination address to the source address, the length, the opcode, the pulse timer value, reserved and CLC. All this was sent using the transmit control we talked about in the last tutorial. So in this tutorial we're going to see how they are being received. So first of all, we're going to see how the destination MAC address is received. How this destination MAC address is received. And remember, when we were sending it in the last tutorial, two things, there was option of sending two things. Either we send the destination MAC address or the reserved multicast. So in this tutorial we are going to see how this receive control checks for either whether this message is going to my MAC address or is for the reserved multicast. So this area, let's watch what happens within this area. I'm going to circle it. Oh, that was bad. Let me circle it again. This area, this is where that comparison occurs. Now these comparators, what they are trying to compare is trying to compare the received data. This is the RX data, the data that was received, with first it compares it with the multicast. This is the reserved multicast. See them, this the reserved multicast divided in bytes. That is 0180 C200 0001. That is the received multicast. So this receive control compares the RS data with each byte of this multicast. After that, it also compares it with the MAC address. I already told you why I separated the MAC address, because Logisim does not have an input that is 48 bits, so I divided it into two, 24. But note you that the MAC address, this input comes from the register. Our MAC address is in the register, so this input is coming from the register, and it's been divided into different bytes into 6 bytes. That is 6 by 8. That is a total of 48 bits. That's the size of our MAC address. So we know that this RS data comes in bytes by bytes, and once it's coming in, we have a byte counter. We are going to talk about the byte counter very soon. It's down here. The byte counter, this is the byte counter. We're going to talk about it very soon. Okay, sorry. This is actually the byte counter, and is the byte counter signal. This is it here. Now let's watch this byte counter signal and see where it goes in. It goes into here. So we are going to talk about this particular area very soon, where this byte counter entered. But note that our byte counter starts counting from 0 once our data reception starts. So here is another comparator. So what it does here is that it compares our byte count with, it checks is our byte count equal to 0. If it's equal to 0, this AND gate should on. If it's equal to 1, this AND gate on. Is equal to 2, this AND gate on. It's trying to know what bytes are we on, what bytes are we counting, so that it could match it with the receive data. So assuming between, since our destination, since this destination address is 6 bytes, therefore once the byte counter is counting from byte 1 to 6, should be the RS data received during the count, this counts byte 1 to 6 should be our destination MAC address. So once after comparing this byte count with these values, all these are in bytes, this 00 is in bytes, it means by 0. So what is trying to tell that here is by 0, byte count 0, byte count 1, byte count 2, byte count 3, byte count 4, 5 and 6. So after comparing and checking if they are equal, then it ANDs it with our detection window. Okay, sorry, it ANDs it with RS valid. Remember when we are talking about the receiver, that the RS valid symbolizes that we have valid data received. Just like we have the byte counter in the receiver, this is the byte counter for the receive control. So this signal here that is being handled with this byte count ANDs it when this RS is valid. So whenever we start receiving data, whether it's control frame or ordinary data, this RS valid is on. So after comparing and knowing which byte count we are on, the next thing it does, oh sorry, I have pressed Ctrl Z in a very bad way. Is there on me? We are good to go. So it ANDs the whole byte count with the, assuming its byte count equal to 0, it ANDs it with the RS valid. That is, the RS valid and the byte count is equal to 0. So this signal, byte count equal to 0, byte count equal to 1, byte count equal to 2, byte count equal to 3, 4 and 5. They all take all of them to this next AND gate. So that is byte 0, 1, 2, 3, 4, 5 to this AND gate, and is ANDed again with our detection window. Remember, mind you, I'm going to tell you how this detection window signal is being generated, but note you, it's coming from our detection window. So if it is within the detection window, therefore the byte counts are equal. So these byte counts are going to turn on these sets of multiplexer. What we are trying to achieve now is to know if the address is okay, the destination address, if this control frame is meant for us or is meant for another frame. So we are actually trying to check, just like when we were doing for the receiver model, we are trying to check if the, let me check again, RS address check. This is exactly what we are trying to do. See all these byte counts, this is the receiver address check. So that's still exactly what we are trying to achieve at this receive control. But at this point, we are no longer checking just for only a MAC address, we are checking for the multicast address. This upper part is the multicast address, this is the MAC address, and mind you, it is now going to put them through a OR gate. Now see this set, and see this range of OR gates. Oh, see the problem. See this range of OR gates where it's odd this multicast. So it's asking whether it's a multicast or our MAC address. If is any of them, therefore we are good to go. The frame belongs to us. I've made this error again. I'm not supposed to press Ctrl Z. Ctrl Z brings back this. So what are we saying? So this OR gates is going to let's take one for example. This one is, it's always this unicast check. So this is where our received data was checked with the unicast 01. That is the first byte of the unicast is 01, or let's take it again, the first byte of our MAC address, you know, is the LSB that is get sent first. So it's starting from the lower part of our MAC address, it's checking for that byte. If it's true, yes, no problem. Then this another one is checking for this second figure, this second byte of the receiving multicast, or the next byte of our MAC address. The same for this, checking for the next value of our MAC address or the next value of the multicast. So these are the things it compares. It compares, is this received data the multicast or is it the MAC address? If it's true, it now comes to this AND gate. Now I'm going to show you what this AND gate does. Remember what we saw when we are talking about when we are dealing with the receiver in the address check. Those AND gates are equal to this AND gate from the receiver, where, remember, during our receiver we do, once it checks the first time, if it's okay, it comes back and checks for the second time, it goes back, comes back again. So what it's trying to tell, what that AND gate does actually is that, where is it, receive control. What this AND gate does is, if doing the first check, after we've compared the first byte and is okay, now take that okay signal and it again with the next check. If the next check is okay, take that okay signal and it again with the next check. So assuming we check the first byte and it was not okay, that is, we checked the first received byte and it didn't match the multicast, it didn't match our MAC address, every other thing is going to fail, because that's okay, that's not okay, that is a signal 0, and that is this address okay here. So whenever it checks, it produces this signal address okay. So if in the first check that this address okay signal is 0, it's going to be 0 for the rest of them. So what this address okay does is to make sure that all of them is okay. So it keeps being okay by checking every single one of them, one after another. Then these multiplexers are turned on depending on which byte count we are on. So assuming we are in byte count 0, is going to turn on, sorry, oh, I've turned this thing on again. So as I was saying, so that is the job of the address okay. It looks is like a feedback. After the first check, it takes the outcome. If it's true, it takes a one signal to the next check. So if for any reason one of the check fails, every other check is going to fail, because the address check loops back the last result back into the next check. So this multiplexer turns on which byte count we are on. Remember, this after this byte count check, it comes here and answers with the detection window if it's on. Then they are being fed into each of these multiplexers. They are the select bits which turns on the multiplexer. So the multiplexer that is on, that is the multiplexer which produces this address okay, depends on what byte count we are on. So assuming we are in byte count 0, that is this one, that means this is the multiplexer that is going to be turned on, and therefore we are only checking for this, because that is the data that is going to be passed through this, and that is what is going to produce the address okay. And when it produces the address okay, it loops back and enters into this next check. When it's byte count 2, this one turns on, we check for this data goes in, comes out again to the address okay, it loops back into the next one. The byte count again comes on. So that is how the byte count checks for our MAC address or the received multicast, reserved multicast. So after doing that check, the next check, remember this is our frame. So after checking the destination MAC address, we check the source MAC address, then the length type. So the next check we'll be checking is the type length. This source address was not checked, is the next 6 bytes. So after we have byte count 1 to 6, to check this length type, we are going to start from byte count 12 to check for this. So minus this 6 during the period of RS data receiving this source address, it will not be checked. So the next check starts from byte count 12 because these two already, the byte count counted the 12. Then this is the next. So the next check starts from byte count equal to 12, and that is for our type length. For our type length. So after that, this is where we did that, where we did the check for our type length. And remember, when we were doing the transmit control, our type length was 8808. Conventionally 8808. That is our type length. So let's see briefly how the receive control does this check. How the receive control does this check. So it passes that value 8808. This is the value 8808. Divides it into 2 because the length of the byte count is 2. So the RS data is going to check for 1 byte on byte count equal to 12, and the next check will be on byte count equal to 13. So let's see how they did this check. We're going to see how this check is being carried out. So let's see. After comparing the received data with this value, it takes this one, let's see, feeds it to this AND gate, and take this one, feeds it to this AND gate, and let's see how these multiplexers are on. 1. Let's see who turned them on. The detection window. As you can see, the detection window, that is what is in charge of turning it on. Whenever this detection window is on, detection window is on, and the byte count is equal to 12. So that is it. It checks. The first set checks byte count equal to 12 and detection window is on. Let's do this check. So it ANDs it with the current value. This is for the second one. Sorry, that yes, byte count equal to 12, yes, and is equal to 8808. So assuming this first one is going to take 88, so it's going to AND it with this. This is to make sure that the byte count is equal to that 12. It ANDs it. So it's saying if this comparator value is true, that is if it's truly 88 that we are getting here and we are in byte count 12, therefore set this signal as 1. So this is how the type length check is being done. So the same thing, this upper part is also checks for the second bytes of the type length. Sorry, this second part here checks for the part of the type length. Then after checking for the type length, we check for the opcode. This is the operational code. We saw it is 0001. So once our transmitter receives this thing through our receive control and finds out that the opcode is 0001, therefore automatically a control frame and not a regular data. So this is where they were compared, 0100 with this RS data. We remember that this is our RS data here. This is it. So it compares to know whether is the correct opcode that we received. So that is that. If it's the same opcode that we received, therefore still the same procedure we did here, that's the same procedure we are going to check. You see, therefore the next thing is going to ask is it within the detection window? If it's within the detection window, is the byte count 14? Because this one's byte count was 12 and 13. So the next one from here, you know that the opcode is the next and it takes 2 bytes. So here is going to ask, is the byte count equal to 14 and 15? It checks. If it's on, here also comes on. So that is the essence of having this byte count check. It checks the byte count against certain figures. So that's basically what it does. So the next check, now at this point, let's see our byte counter. This is the main counter of this receive control. See and understand how this our byte counter works. This is it. So let's see what resets it. The signal that does the reset is the RS end from signal that does the reset. That is at the end of data reception, RS end frame. That is, it is done receiving signal, therefore reset. Now let's see what turns it on. There's a bunch of signal that turns it on within this AND gate here. This is where it can be turned on, but let's see the signals that turns it on individually. 1, the RS must be valid. This is it, RS must be valid. Then 2, this signal is going to be off. What signal is it? Let's see. Let's see the signal that is going to be off. The byte count is equal to 18. This is it here. Byte count equal to 18. So whenever it counts up to 18, and once the byte count counts up to 18, stop counting. We have reached the end of the counter. So remember, we are still talking about this our byte counter. It says whenever is up to 18, and so 18 is the last byte count, is it? Remember, this is 12 already plus 6, this is 18. So we didn't include this remaining part, the reserved and the CLC. So assuming you added values for this remaining part, that means your byte count will almost be reaching 60 something. That is probably 64 or so. So because we didn't increase it, whenever our byte counter reaches 18, it resets. That's the end. That is how this one works. Then also, so okay, so that is okay. No, not just that it. Then we have to be within our detection window. That is another signal, being within the detection window before we do this reset thing. Then I think this one is for the delay CLC enabled. We talk about that too also. So this is how this our byte counter increments. When you go to the code, you see it. So there are other okay, now let's look at our detection window. How does this detection window come on and off? How does this detection window come on and off? So this first signal turns it off. Let's see what signal turns it off. Byte count is equal to 18. So whenever the byte count also equals to 18, it means turn off everything. We are done receiving the control frames. We have received all the control frames. So reset everything. Reset both the detection window, reset both the byte counter. So now let's see what sets it. What does the setting? So to set it is this receive end. So what is this receive end signal? We are going to see this receive end signal when we will be dealing with the mark status. Receive end marks the end of data reception. It's more like the RS end frame. But when we will be dealing with the mark status, we are going to see how it ends. So once the receive frame ends, turn on the reception window. That is what it's trying to say. Once our receiver is done receiving data, let us turn on. That is the period of detection window. That is the period we assume to be our detection window. So you can't start detecting control frame when the receiver is actively receiving data. You are only going to check, turn on your detection window after data reception, not doing a current data reception. That is why to turn on this our detection window, we use this receive end. When we be dealing with the mark status signal, you are going to see how this receive end actually comes from. But just note that is at the end of the data reception that receive end comes on and turns on our detection window. So then again, this particular we've talked about. Okay, let's talk about this signal, the receive pulse from address. This signal here, this signal comes on after all the whole check. Okay, but let's first of all see what turns it off. Let's see what turns this particular signal off. The receive end. So whenever the end of frame reception turn this signal off, we call it received pulse from. Receive pulse frame. That is receive pulse frame. It marks the end of. Let's see how it comes on. When these are the criteria for turning it on. After the whole check, which we did here. After checking for MAC address, type length, opcode, byte counter, and the rest. If they are all okay, therefore turn this bit here okay. So this bit here is a combination of all the OKs. It compares the address OK and includes all these little OK, the type length OK, and the opcode OK. So the three of them comes here and adds together. If all of them are all okay, let's turn on this received pulse from OK. So that is how it comes on. So this video is 33 minutes. I'm going to cut it, and in our next tutorial we are going to see how we did this, how we generated this. So please subscribe to my channel, and thank you. God bless.